This video I will introduce online learning concept. This is very interesting and very important in computer science. So what is online learning? Until now we have discussed batch learning algorithms where the learner first received a batch of training examples, and after the learning process the learned hypothesis predict the output of new examples. Okay, in other words, we first collect a training data set, so which consists of many input and output pair. Let's say x1, y1, x2, y2, and so on. And then using this training data set, we find some best hypothesis among our hypothesis class, that is training process. And then after the learning process, the learned hypothesis predict output of a new example. And most of the case, we assume that the training data and the test data follow the same distribution. Okay, so there exists some data generation distribution D, and all the input and output pair comes from this distribution. That is main assumption of batch learning and classical machine learning process we have discussed up to now, until now. So today in this video we will discuss online learning concept. This is a little bit different. Instead of batch of data, a sequence of consecutive learning round will be there. Okay, so repeatedly at time t equal to 1, we first receive a new instance, let's say x1, and then the learner predict the output for the instance x1. Okay, and then after each prediction, the learner receive the correct label y1. Okay, first receive the instance and then predict and then receive the correct label, so we can check whether the prediction is correct or not after the prediction. So after the first round, we can learn something from the first round information. So maybe we can update our prediction function so that we can do better for the next round. So at time t equal 2, we repeat this process. We first receive a new instance x2 and then predict and then receive the correct answer. So using this information, we can update again our prediction function, and time t3 again receive new instance, predict, and then check the result. This is y3. This is online learning process. Okay. So for this course, I wanna define useful notations. First, I will use xt to denote the instance given to the learner at time t, at round t, and pt to denote the predicted label by the learner, and yt is the correct label. Okay, so here the learner score is, of course, we want to minimize the number of misclassified example instances, so make as few prediction mistakes as possible. So this is some very important notation, MAH, which denotes the maximum number of mistakes by an online learning algorithm A. So here A denotes the algorithm, and of course the maximum number of mistakes depend on the hypothesis class what we consider now. Okay. Of course, when the hypothesis class has many hypotheses and very complicated, then MAH will be high, will be large. But if our hypothesis class is very simple, only few hypotheses there, then MAH will be very small, very tiny. Okay, so it depends on the hypothesis class. So we will discuss later more accurately, more properly, more precisely. Okay, so here we consider data models like this: IID, deterministic. So we usually assume IID data generation model for batch learning case. So there exists data generation distribution D, and we let's say sample n training data point from this same data generation distribution, and the test instances also comes from this same distribution. That is one of very important assumption for the batch learning cases. Okay, for the pack learnability, when we define pack learnability, we usually define such probability for the data generation process, and we usually assume that all the data instances comes from the same distribution independently, identically. Another example of data model is deterministic model, where the data instances just given by some deterministic way. Okay, and more extreme case, there exists adversary. Adversary means we can adaptively control the input instances based on the learner's predictions up to time t-1. The instance xt and the up yt can be arbitrarily, which can also be controlled from the information x1 through xt-1 and y1 to yt-1. And even the yt can be changed after we observe pt. The adversary can freely control xt and yt. That is adversary. Okay, so here we consider adversary game for the online learning, and we want to optimize the performance even with the adversary game setting. So what is adversary game? So there exists learner and adversary, and the adversary can wait for the learner's prediction and then provide the opposite label as the correct one. So adversary can make the learner always false. Okay, the number of prediction mistakes, of course, therefore can grow arbitrarily large. Okay, so very extreme case of learner versus adversary. This is not fair ground. Adversary can always win because the online model, what I introduced right before, was at each round we observe instance, the learner observe instance, and then the learner predict the PT, the label, up label, and then the learner receive the correct label YT. So the adversary can make YT always not equal to PT. So that is a winning strategy for the adversary, because the adversary can observe both XT and PT always. So adversary can always win. So this is not fair rule. So we need some more restrictions. This is the first restriction, realizability. So labels come from some hypothesis, a hypothesis among our hypothesis class. Okay, so the adversary can say at least one hypothesis in our hypothesis class that can explain all the previous instances. So which means at time t, if you want to make yt for the instance xt, you have to, the adversary has to have function h or hypothesis h that has this property not only this property, but also all the yt minus 1 is equal to hxt minus 1 up to y1 equal to hx1. Okay, so there exists at least one hypothesis that can explain all the instances and label pair. Otherwise, the adversary is failed to be the participant of the game. So the adversary is out. Okay. So the adversary has to follow this rule, realizability. So when adversary make yt operable, there exists at least one hypothesis that can explain all the input and output pair up to time t. Okay, but the adversary can choose both hypothesis and the sequence of instances. Okay, the adversary not only control the yt but also control xt. So after all the predictions and outcome of yt, based on this information, the adversary can also control xt plus 1, and from the pt plus 1, the adversary can control yt plus 1. And h star can change all the time when the h star can explain all the previous instances as well. Okay,